So this is Muskan Fatima of CSC branch roll number 22951805B5 from section B. Today we are going to discuss about basic electrical engineering tech talk, and our topic will be superconducting DC generators and motors. Let's get started with superconducting DC generators. We'll be knowing about introduction to superconducting DC generators and motors. So, introduction. Most of today's superconducting DC generators were designed for energizing large superconducting electromagnet systems, for energizing multiple concentric coil magnets by single pumps, and for energizing tuning magnets by a system having adjustable tuning control 1 to 5. The chief advantage of the DC generator is the avoidance of the large input IDLs that will be required to carry heavy currents from external sources to superconducting devices, because these LEDs can produce high heat losses. The problem becomes more significant as superconducting wires having higher current carrying capacities are developed. Another potential application of superconductivity where the input LED heating problem is critical is in the input and output devices required for superconducting power transmission systems. So, another potential application for superconductor where the input LED heating problem is critical is in the input and output devices required for superconducting power transmission systems. 6. 7. At present, it is thought that because of the AC losses that have been measured in superconductors 8 to 12, these transmission systems must be of the DC type. Another method for avoiding the input LED problem is to generate the direct current at a low temperature by use of a superconducting DC generator. The torque input could be supplied by means of a thin-walled, large diameter tube rather than a rod with a larger cross-sectional area that would be required for the same torque. This geometric factor gives an additional degree of freedom with which to minimize input LED heat leaks. Alternatively, lower overlosses might result if the input were produced electromagnetically by a motor having a room temperature stator and a thermally insulated low temperature rotor. The DC generator also could be reversed and used as a motor as the transmission line termination to extract the energy. Now, what is a simple DC generator? As we can view in the figure 1, it shows a simple DC generator consisting of a sheet of low critical field superconductors such as lead, to which is connected a loop of high field superconductor material such as niobium tin. It was necessary to develop special techniques for making the superconducting joints. A permanent magnet rotates about an axis so that its path traverses the lead sheet as shown. Its distance from the sheet, its pole shape, and its strength are adjusted in such a way that a normal spot will be produced in the superconducting sheet by exceeding the critical magnetic field at the operating temperature. So, this spot is penetrable by magnetic flux, whereas the remainder of the superconducting sheet is perfectly diamagnetic and expels magnetic flux. As the magnet is rotated counterclockwise, a normal spot of material forms at the edge of the superconducting sheet and is drawn across the sheet by the magnet. That is, magnetic flux is trapped in the normal spot and taken across the sheet. This flux is surrounded by a closed superconducting loop consisting of the lead plate and the niobium wire, and thus a persistent current is induced in the circuit. As the magnet completes the cycle, it crosses the niobium tin wire. However, it is not switched normal because of the high critical field of niobium tin. The figure 2 explains the detail of superconducting sheet in which the movement, normal spot, and fixed element is shown. Operation of a DC generator. Let us now consider the means for inducing the persistent current. Figure 2 shows a fixed resistive element in the normal spot. As the normal spot is moved, flux crosses the element. A complex written path is provided by other elements, including the remainder of the lead plate, which is superconducting but still has inductance, in the niobium tin loop. The essential elements are shown in figure 3 and 4. The work done by the torque that turns the magnet compresses magnetic flux into a higher field, higher energy region. The torque is proportional to the speed, and so is the Faraday electromotive force generating the persistent current if the magnet is stopped. The EMF is removed and the persistent current remains at a a constant value. As shown in figure 3, equivalent circuit for inducing persistent current showing the essential elements schematically. Now, note that the persistent current is being altered by the Faraday induced current all the time. The magnet is crossing the sheet, and that there are no large edge switching effects. Although the flux trap within the loop changes discontinuously, so does the total loop inductance, and a smooth variation of current is therefore produced. In the calculation of energy changes in the system, inductance changes caused by the movement of the magnet must be considered, as must the current changes. Power generation. Let us now calculate some efficiencies for DC generators, such as those that might be used for energizing large superconducting power transmission lines. The terminating load will be reflected in the superconducting loop, and power will be dissipated in the load at the same rate that it is being introduced by the generator. The power generated by a DC generator is 1A power CO2 dt ergs per second. Thus, this is power watts is equal to 2dt 10714. Consider the generator design shown in figure 6, that is a typical DC generator design. The sheet is in the form of a cylinder of radius r centimeters with a small gap parallel to the axis and contacts to the loop or the load at the ends. The magnet rotates inside, producing a normal spot with the dimensions of y by z centimeters as shown. Soft superconducting sheet. For a soft superconductive sheet, the current carrying capacity is 7 is equal to this and this amperes to 7t. For maximum power generation, 6 is equal to watts, and therefore I is equal to minus HCR amperes. Let us now calculate some efficiencies for DC generators, such as those that might be used for energizing large superconducting power transmission lines. Mechanical losses at low temperature will be magnified because of refrigerator inefficiency. These losses therefore must be kept small by the use of superconducting bearings to reduce bearing friction, and an aerodynamically smooth rotor to reduce viscous heating, which should be small in any case because of the low viscosity of liquid helium. The AC losses of superconductors are usually small because only a small ripple current is generated. If desired, this ripple can be further reduced by the use of multiple magnets. There may, however, be a loss because of the finite velocity of the normal spot across the sheet. That is, the normal spot may move an appreciable distance in the time that is required for the superconducting to normal phase transition, and second order eddy currents may be produced. The effect of these eddy currents can be reduced by laminating or slotting the superconducting sheet parallel to the direction of current flow and across the direction of motion of the normal spot. The laminations, which would cover the normal spot but not reach the edges of the sheet, also introduce a desired anisotropy in the sheet of resistance. So, power generation can be classified by this. In this diagram proves it. The normal spot is in the middle. In the center, the low field superconducting sheet is used. Superconducting joints are shown. A small gap is present for the easy movement of the generator. High field superconductors to load are present for us. And here goes our conclusion part. Large superconducting DC generators can be designed for low losses. They could serve as ideal input devices for DC superconducting power transmission lines. In reverse, they could be used as a motor to drive room temperature AC generators at the outputs. They also may be employed as input-output devices for inductive energy storage systems using superconductive electromagnetic coils. Here we have a diagram. So in this diagram we have a DC generator, which is a high motor which is used for transfer of water from low energy level to the high energy level, that is from a low portion to a high portion. There we have brushes, yoke, stator, shaft, armature, commutator lugs, commutator bearings, so that it gets easier for the water to transfer from ground level to higher levels. Generators are mostly used in industries for the transfer of water or chemicals from one place to another or from one area to another area without any abruption. This uses much energy, but it is better than AC generators, which are very big and large. These are very small, and we can, it's very comfy to take it from one place to another. These DC generators are helpful, and these motors help in daily day lives of many poor people. As we see, as a like daily life example, we can see that every house has a motor. Every building house has a motor to transfer water from ground level to the tanks that are situated up on the top floors, like it may be first, second, third, or fourth, any. So the water can be transferred from ground level to the top level without any problem through this motors, which are created by DC generator plant. So I guess this will be the end of the session. Thank you, and thanks.